Hello, ladies and gentlemen. Our project is deep learning methods for task classification. First, I will introduce the task of task classification. Task classification is one of the fundamental tasks in NLP. The goal is to assign labels to tasks. It has broad applications, including sentiment classification, news classification, natural language inference, question answering, and we will focus on sentiment classification. Then I will introduce the dataset we use. The Stanford Sentiment Trainback is a binary single sentence classification task consisting of sentences extracted from movie reviews with human annotations of their sentiment. SST2 is partitioned into three sets with the size of 72%, 9%, and 19% as training, development, and test sets respectively. The proportion of positive and negative examples is 3 to 7. Here is an example. That's found for kids of any age. It's a positive sample, and the movie is well done but slow is a negative sample. This is the distribution of sentence length. It is important to know the max length because we need to choose the max length as one dimension of batch data and do padding and masking. Now I will make a brief introduction of embedding. Embedding is an important part of feature extraction. First, we build a vocabulary and we can get a word index. Then we use the pre-trained embedding vectors to initialize in the embedding layer and get word vector. We also try char embedding. Characters are fed into CN encoder. We can also use RN to do an encoding, and then concatenate char embedding with word embedding. Then come to the deep architectures. First, I will talk about the deep learning task classification system we implemented. It mainly contains 5 modules. This is used to parse the command line to read parameters. Each hyperparameter is set with the default initial value, and the prompt message is given. Data is used to store the dataset and word embedding metrics. This part is designed for reading and pre-processing data. The key point is to convert the dataset into instance. Each instance contains the label and the word list of a text. After data reading and pre-processing, batch data is generated, and the maximum sequence length is selected for padding and masking. This part creates a vocabulary after filtering out low-frequency words and realize the map functions from word to index, index to word, label to index, and index to label of word embedding matrix. This is the most important part, where universal RN encoder is implemented. It is worth mentioning that we achieved this encoder with cells as the smallest units instead of using RNN, LSTM, GRU from touchpoint and endpoint module. The biggest advantage is that we can conveniently slice the network with the cell as a unit. Our task classification system can be easily run on the terminal and quickly adjust hyperparameters. In addition, the network structure can be printed out to facilitate analysis and visualization. You can see our GitHub for more details. We realize these models in our task classification system, and we will introduce these models later. Then I will introduce the RN-based model. First, We slice each text into words, word 1, word 2 to word t, then map each word I to a word vector ei based on embedding matrix from pre-trained word to vector. At the next step, these word embedding vectors are fed into Rn-based cell through time, and we get a hidden state vector ht, and then we use backward RNN to read the text from word T to word 1. The text representation V is obtained by applying mass pooling on the concatenations of the forward hidden state and the backward hidden state in each timestamp, and then put a vector to softmax. By the way, the Rn cell can be replaced by L16 cell and GRU cell. Then I will introduce the CN-based model. RNNs are trained to recognize patterns across time, while CNNs learn to recognize patterns across space. RNNs work well for NLP tasks such as part of speech tagging or question answering, where the comprehension of long-range semantics is required, while CNNs work well where detecting local and position-invariant patterns is important. These patterns could be key phrases that express a particular sentiment like, I like this movie very much. Thus, CNNs have become one of the most popular model architecture for text classification. Here we use text CNN. Text CNN is a model which uses a series of convolutions which kernel size is 2, 3, 4 to extract the features.
Okay, then I will introduce the attention mechanism. And the picture shows the word embedding and the encoder part are just the same as those in the RN-based model. So the special thing is the word attention part. First, we fed these hidden states through a one-layer MLP, which is multi-layer perceptron with 10H activation function to get Ki and hidden representation of HI. Then we create a learned context vector QW and compute the inner product of Ki and QW to get the attention weight AI. Finally, these weights are used to produce the final representation vector V, which is a weighted linear combination of the hidden states. And this is a code of attention mechanism. As we can see, the biggest advantage of attention is it's easy to be visualized. We choose some samples from the test set and use trained by LSTM attention model to do some visualization. The color intensity of each word means how much attention the model pays. It's clearly seen that the model could capture sentiment words such as beauty, wonderful, and spectacular to identify if the sentiment of the sentence is positive or negative. The next model I will introduce is BERT. Here, I will only illustrate how BERT can be applied to text classification tasks. First, BERT has its own tokenizer, which can split a single sentence into many tokens. It's interesting that BERT tokenizes some words into many tokens, just as the picture shows. After tokenization, each token is converted into an input embedding, which is the sum of token embedding, segment embedding, and position embedding. Then we fed this input embedding through multi-layer transformers and use the output embedding of CLS token to predict the label of the sentence. So this is the code to convert dataset into tensor that could be input for training BERT. For better understanding, we take these 5 sentences for an example. First, we set the maxima sequence length to 20 and tokenize these sentences into tokens. Then we concatenate CLS token at the beginning of each sentence and do truncation and padding based on the maxima sequence length. Finally, we can return token embedding IDs, where the ID of CLS is both 101 and padding is 0. We can see that the tension mask of padding is also 0, which means this padding will not be considered during self-attention. This is the main code for how to training BERT. First, we shuffle the dataset and split it into batches. Then we reset the gradient to 0. After that, we do the forward part of BERT model and return the loss. Finally, we backpropagate the loss and update parameters. Nowadays, there are many variants of BERT, and we list some of them. You can see the number of parameters are already large for base size, and even more for large size. In the fifth part, we did lots of experiments to compare the performance of different models. You can see there are lots of hyperparameters for a single model, so it's really hard for us to find the best one. And our method is to use grid search combined with random search to tune the hyperparameters. And this is our final result, which shows the accuracy on test set of each model. These 4 are RN-based model, and the white one is CN-based model. The purple is bi-LSTM plus attention, and these 4 are BERT, Albert, Robert, XLNet model with base size. These 4 are base size plus text attack, which are slightly better than base size. Finally, these 4 are large size. We can clearly see from the picture that robot large model gets the highest accuracy of 95% among these models. After experiment, we also summarize some tricks for training deep networks. For RN-based and CNN-based model, we use ADAM optimizer with initial learning rate equal to 1e minus 3. The batch size needs to be adjusted appropriately. Generally, it's often not exceed 128. For test CNN model, the kernel number is often set from 100 to 600. And for LSTM, the hidden size could be set to 150 or 300. And for BERT-based model, learning rate is the most important hyperparameter, which is often set from 1e minus 5 to 1e minus 4. It's recommended to use learning rate warm-up during training. Finally, I will summarize our work and the prospects for future work. In our project, we learned and wrote thousands of lines of code and built a deep learning text classification system. In the process of training, we implemented different models and their variants, including our self-right bottom layer algorithm. Finally, we conducted comparative experiments and summarized the training skills. This is a timeline for the research of text classification. As early as 1961, the field of test classification began to develop. Few years later, the famous KNN model was brought out by Thomas Culver and Peter Hart. This model is still very popular today. Decades later, SVM, RNN, CNN, LSTM, and their variants were also born. Until recent years, the famous BERT model has also surfaced, and the variants based on it had merged in endlessly. So there is still a long way to go. That's the end for our presentation. Thanks for your listening. Our code is available on GitHub. You are welcome to say and start. Thank you.